So this week we're talking about waves. You can read all that. So a mechanical wave is something moving through a medium. We have two different kinds of waves we can have. We can have what are called longitudinal and transverse waves. So a longitudinal wave looks like this, where things are moving back and forth as the wave moves down. So this is also called a pressure wave. So if I got this piston going back and forth, that's compressing the water and then decompressing it, compressing it and decompressing it. So the individual particles in the fluid would be moving left and right. And then those high pressure areas would propagate through the fluid in the same direction the particles are moving left and right. We call that a longitudinal wave. Sound is a longitudinal wave. Any kind of compression wave is a longitudinal. A transverse wave, the individual particles move up and down while the wave moves left and right. Think of like if you're watching the ocean and you see a wave go by and you watch a seagull just go up and down and up and down. So the seagull's not moving left and right, even though the wave is. So in longitudinal, everything's parallel. The particles move in the same direction as the wave front. In transverse, particles move perpendicular to the wave front. In these transverse waves, the only thing that's moving left and right is energy. Energy is being transferred. And then you can have combinations of the two. Like if you were to play this game here, you would end up with both kinds of waves mixed together. Like think of the crowd doing the wave at a stadium. Individual people are not moving left and right. They're standing up and sitting down. Literally nothing is moving left and right except the energy. The disturbance is moving through the crowd. Okay, now you don't have to have periodic waves. Like that was not a periodic wave. That was just what we call a plane wave. It was a big disturbance that moved and then stopped. It didn't keep going. It didn't repeat. Periodic waves are much easier to study though. So we're going to spend most of our time studying periodic waves. Okay, so you're going to want to write all these symbols down. The key to understanding waves is knowing what all the symbols mean. And we're going to have a bunch of them. So I'm just going to kind of gloss over them today. And then next time we'll literally write them all down and do some examples with them. But lambda here is called the wavelength. F is called the frequency. V is the wave speed. When we say wave speed, we mean how fast is the front of the wave moving? How fast is energy being transferred? So if we go back to our stadium here, I don't mean, when I say wave speed, I don't mean how fast does Bob stand up and sit down. Not how fast is something going up and down. How fast is the wave moving through the crowd? So when we say wave speed, no actual particles move at the wave speed. Energy moves at the wave speed. Like for light, light is a wave. Do you know what we call the wave speed for light? Just take a guess. The speed of light. Okay, so imagine if we had this scenario. We got a mass on a spring here, simple harmonic motion. Remember that from last semester? We let this thing bounce up and down, and it's attached to this string. So that's going to create a wave that changes in both position and time along the string. These are called crests. The tops, the bottom are called troughs. The distance from one crest to the next is what we call the wavelength, the distance in space. So the string is bouncing up and down, the wavefront is moving left and right. It's a transverse wave. You could also have periodic longitudinal waves, like a note on a guitar would be a periodic longitudinal wave. So you got this piston in some periodic fashion, compressing, decompressing, and so forth. Then what travels, the wave itself, are these compression regions. These regions of high compression move along. So these would be our crest, and these places of like near vacuum or low compression, rarefaction, would be like our troughs. Okay, so one way to have a periodic wave, this is not the only way. I don't want you to get the impression that all waves go like cosines. They can all be modeled after cosines. Somebody asked earlier about Fourier transform. We can approximate all waves using an infinite sum of sines and cosines. But we're saying, let's pretend we have this scenario right here where something following simple harmonic motion is building our wave. Then we'll have a wave that follows this formula right here. Okay, so let's break all this down because all of these, this is the most important slide in this entire lecture. What I'm describing here is the vertical position of this string, and that's a function of two variables at a certain position at a certain time. So y here is a function of position and time, and we're assuming it goes like a cosine. We could have just as easily used sine here, but cosine is friendlier. Amplitude is the maximum distance. So if we go back here, our amplitude would be this distance from the midline to the crest. You guys have taken trig. So literally this is everything you did in trig in 2 dimensions instead of 1. We have 2 independent variables. Then we have, look here, where I've got 2 independent variables, x and t. In front of t, we have this thing called omega. That's our angular frequency. And in front of x here, we have this thing called k. That's our wave number. Now, I want you to think back. I am going to need to get my projector out. I want you to think back to when you took trig. I know it's been a few years and you've probably forgotten most of it. But remember the basic form for graphing cosine? A cosine bx plus c. Here's where the cosine comes from. We've got this mass on a spring, and I'm letting it bounce up and down and up and down. It's attached to this string. So that's what's making the string bounce up and down. And this is a snapshot. I've taken, say I'm at t equals 5 seconds. I let this thing run for a while. It's bouncing the string up and down. And I took a picture of it, a Polaroid. And this is what the string looks like at that time. Now imagine what I want to talk about here is, let's pick this spot right here, that position. I want to describe what is the height of that spot right there at that position at that time. That's what this models. Well, why does it look like a cosine? Because imagine if you get a flashlight and shine a flashlight on this block right here and look over here on the wall and watch this thing go up and down. Well, it's going to start out up here high. It's going to go low. It's going to go high. The shadow is going up and down like this. What if we got out one of those seismographs or like a polygraph? You guys have all seen polygraphs where you have paper running through. And imagine I've got a marker right here as paper is flowing over like this. What kind of drawing am I going to draw on that? So this thing's bouncing up and down. It starts high, it goes low, it goes high, it goes, it's going to draw out a cosine. That's why this ends up looking like a cosine. And also because if you take a snapshot, it looks like a cosine. So let's think back to college trig in one dimension. Forget about looking at this in terms of x and t. Let's just go back to trig when you learned y equals a cosine of bx plus c plus k. That was your vertical shift. That was your phase shift. We don't have either of those here, so we don't have to worry about those. You guys remember what B stood for? College trig, you don't remember? That was related to your period. Your period was 2 pi over B. Period meant distance from one crest to the next in space. We give that a different name here in space. Period for us is going to mean time. So in trig, you might have called that period. Instead, we're going to call that the wavelength, lambda. So lambda is our wavelength, and it's the physical distance from one crest to the next. Whatever number is sitting here in front of x is 2 pi over lambda, our wavelength. That number, though, if we think it back to that polygraph machine watching this thing oscillate up and down, that depends on how fast this thing is oscillating. Another way to think about simple harmonic motion, literally another way to get the same picture, and you should have seen this example back in Physics 1, is to imagine a record player spinning around. So you've got a record player spinning around with a marker attached to it. And now you've got that polygraph machine or that seismograph running paper over top of the marker. So imagine this guy spinning around, and I'm taking paper and just feeding it across. What kind of graph is that going to draw on the paper? It's going to graph a cosine. Because I'm starting high, all the paper is going to measure is how I go back and forth like this, because it's going like this. That how fast this record player spins determines how quickly I wave back and forth, which is equivalent to how fast this thing oscillates up and down. When we talk about things rotating around, we measure them in how fast, how many radians per second they're spinning. So we call that omega the angular frequency. And that's in radians per second. That's this guy right here. That's B. Oh, no, sorry, that's K. Okay, so we've got this guy here that is a function of two variables. Omega here is this guy I was talking about. That tells you how fast this thing is moving up and down. K here is the equivalent of that, only in space instead of in time. So we've got this great picture here from the book that puts all this together, if it hasn't logged me out yet. If I don't change pages often enough, it will log me out. So let me do that. Okay, so this kind of puts everything together here. So I've got that oscillator bouncing up and down. We're going to follow it through an entire cycle. See, it starts up just arbitrarily. We decided let's make it start up. See, it's moving down, gets all the way down to the bottom, and then comes back up again. That's one complete cycle. Or what are we going to see as the viewer? So imagine this thing's been bouncing long enough that there's wave all the way down. So this initial spot right here starts at the top, goes to the middle, goes all the way to the bottom, and goes back to the top. If I were only watching this spot right here, I'm fix my x equals 0. I'm at position 0. Then in time, I'm watching a cosine graph. Or if instead I fix my time, say I pick this time right here. So time is frozen and I'm just looking at the different x's. Some kind of sinusoidal cosine graph. So it goes like cosine in both time and space. So let's watch this position right there. It starts down, goes to the middle, goes all the way to the top. By the end of a cycle, it's back down again. That one particle has been moving up and down. The wave moves left and right. The distance in space from one crest to the next, so this distance right here is what we call the wavelength. The equivalent idea in time we call the period. So the time it takes to get from here to here is the period. Okay. I'm going to write all that down. Questions? Our wave formula, which depends on x and t, is a cosine kx minus omega t. We can look at it at a fixed time. We could say, I don't know, maybe t equals 0. Y of x comma 0 would be a cosine kx, because t was 0. Then we would get some wave in space here that looks like that. That's just a snapshot of this thing bouncing up and down. This distance from one crest to the next is the wavelength. That's measured in meters. It's the physical distance from one crest to the next at the same time. Wavelength in meters. And k here is 2 pi over lambda. That's the number that goes in the cosine. That's called the wave number. We don't do much with K in this class. If you become a physics major, you do more with K. This is probably the last time we'll mention K. It's not as interesting. Now let's play a different game and look at just a fixed position. Let's say x equals 0. So this whole term here is 0. We'll get y equals, I'll have a negative in there. But remember, cosine's an even function. I can actually ignore that negative. So I'm just going to erase that negative. Cosine's an even function. Cosine of 30 degrees is the same as cosine of negative 30. But what I want to point out here is now we have y versus time. We're watching one particular spot move up and down. So back here on this graph, so I'm watching this spot right here. I picked x equals 0. It could have been anything. I'm watching this oscillator bounce up and down. So y versus t will get something that looks like this. It still looks like a cosine, but now we call this distance from one crest to the next. We're measured in the time universe here. We call this the period, t. It's the same concept, but now we're measuring distance in time instead of distance in space. That's measured in seconds. This is literally how much time it takes to get from one peak to the next. The reciprocal of that, 1 over t, we call the frequency, little f, and this is in hertz, cycles per second. So when you tune in, you're in your car and you tune into the radio, 101.6, that's 101.6 megahertz. So times 10 to the 6th hertz, cycles per second. Pitch, anytime we're talking about the pitch of a note, that's directly proportional to the period. Or sorry, that's directly, I did it inverse, directly proportional to the frequency. Pitch and frequency mean almost the same thing. Whether you're talking about physics versus music, that's really the only difference. Pitch and frequency are the same thing. How are all these related? V equals lambda F. That's the relationship between time and space. Because remember, that's meters per second. Lambda is measured in meters. Frequency is measured in cycles per second, or 1 over second. And remember, omega equals, let's say it this way. The period equals 2 pi over lambda. I want to get these right. 2 pi over omega. Lambda equals 2 pi over k. F equals 1 over t.